In this video, we actually leave the real numbers and jump into the world of imaginary numbers. Get ready, we're talking about complex numbers and completing the square. Let's get started. To begin, I want to remind you that sometimes you have an equation which is not linear, right? We're actually going to spend some time on this a lot this semester where we have degree 2 or degree 3 equations. How do we solve them? So take a look at this one. X squared equals 9. It's really saying what squared, because x is unknown, right? What times itself would give you 9? You intuitively know the answer, right? 3, right? 3 times 3 is 9. But there's another answer that you might have missed. Can you think about what it might be? -3. Did you think of that? Maybe not, but hopefully you will by the end of this video. -3 times itself is also positive 9 because a negative times a negative is a positive. So it turns out that 3 squared equals 9, but also -3 times itself equals 9. So we would say that x should equal, watch out, here's a new sign for some of you, plus or minus the square root of 9, which is 3. Interesting. So x is positive or negative. That's what that symbol means. Side note, I once went to buy a cake at an ice cream place where they sell cakes, and my mom's birthday was not one of the candle options they had, so I said, could you go ahead and put plus or minus 10? They didn't know what that meant, and it made me so sad. Don't be that person. Know what plus or minus means. Positive or negative, that's what it's saying. All right, so let's continue with where this comes from in a general sense. When we talk about the square root property, which is what you see on the left side of the screen, it says if b is a real number, then if you have something like a squared equals b, a must equal plus or minus the square root of b. In other words, in simple terms, if something squared equals a number, to get rid of the square, you have to take the radical, the square root to be precise. But it's not just the positive square root. It has to be the positive or the negative, because when you raise a power to an even power, it'll always become positive whether you started with a negative or not. That's why you end up with the plus or the minus. Notice if this had been a x cubed situation, maybe equals 27, the answer would just be the cube root of 27, which is 3. It wouldn't be the negative cube root, because when you take a negative to an odd power, it becomes negative. It doesn't stay positive. So this is always going to be our protocol. When we have something squared equals a number, we take plus or minus the square root of the other side to get rid of that power. But look at what happens, this is where the imaginary numbers pop up, when we have x squared equaling a negative number. So if I have x squared equals -9, let's think about what that's asking. It's saying what times itself would give you a -9? Well, 3 times itself gives you positive 9, right? We just talked about that. And -3 times itself also gives you positive 9. So how would you ever get -9? If you're thinking that this sounds fishy, you're right. It's not possible for any real numbers. That's why in math, when these types of equations pop up, we need a way of talking about them. And mathematicians a long time before us decided that the way they were going to talk about them is using a symbol called I. I stands for an imaginary number. To be precise, here is the imaginary number it stands for, the square root of -1. Anytime you have a square root of -1, we call this I, the imaginary number I. Now, we're going to use I as a placeholder, if you will. It's a lot easier to write I than the square root of -1. It's a lot cleaner. It means it's not real, but if it pops up, we want to have a name for it to keep track of our terms, okay? So what will happen is, in this class and in future classes, when I pops up, you need to know how to combine terms that have I, like 2I plus 3I is 5I. Also, what happens if you multiply i's? An imaginary times an imaginary, it turns out to be a real number again. Take a look at this. I times itself is also known as I squared, will always equal -1. So you can memorize those two fun facts, but I want to show you why the second one is true. If you took I, which is really the I times I here, I is really the square root of -1, times I, which is the square root of -1. If you go back to our last video, if you multiply a radical by itself, it lifts the radical, doesn't it? You just get -1 because there's two of them. There's a pair. Right? So I times itself, I squared, will always be -1, and that will be important to us later in this course and in future algebra-based courses. So keep in mind, if you're dealing with a radical situation and you're trying to simplify a radical, if you have a negative under a square root, that really is just I in front. For example, if I had the square root of -4, what would that be? Well, that's really, if you think about it, the square root of -1 times 4, isn't it? So I could break it into pieces to show you where this is coming from. And that's really the square root of -1 times the square root of 4. If you remember from our previous video, we multiply, we put them back together, and here we take them back apart. That's really I times the square root of 4. But what is the square root of 4? It's 2. So I times 2 is also known as 2I. So that would be 2I. For our answer to the problem above, if you had x squared equals -9, you could try the square root method, right? You could say, well, x should equal, in theory, positive or negative square root of that number. That's the square root method that we just talked about at the beginning of this slide. But we just mentioned that a negative under a square root is not possible. That means we have an I in front. So we really have plus or minus, positive or negative, I times the square root of 9. But the square root of 9 is known to be 3, because 3 times 3 is 9. So I could really write this as positive or negative 3 times I, or 3I. That seems kind of crazy, I understand, but keep in mind, if you now multiplied, if you plugged it back in to see, is this truly x? Well, yeah, take a look at positive 3I times positive 3I. That would be 3 times 3, which is 9, and I times I, which is I squared. But what is I squared supposed to always equal? -1. So -1 times 9, we're back to -9. So yes, in fact, 3I squared does give you -9. What about -3I squared? Well, I'll just pop the sign in there, you can see what happens. Maybe you already have an inkling about what might happen. If this was a -3I, and you squared it, -3 times -3 is still positive 9, isn't it? So you're back to 9I squared, you get the same answer ultimately. All right, so that might be crazy talk for many of you. If you've never seen I before, I'm sorry, but here it is. I equals the square root of -1, and I squared will always equal -1. Okay, gotta have that fun fact in your reserves anytime you see a square root of a negative number. If you're already doing some thinking, what about a cube root of a negative number? Those are okay, those are real, because you can take a negative to an odd power and get a negative result. So those are real numbers. It's the even index that we can't have negatives underneath. Okay, so feel free to watch that again if you need to refresh what's going on with I. But we're going to head over to our next slide if you're ready and talk about how to work with these complex numbers. So in example 1, we say write each expression in terms of I. They could have also just said simplify over the complex number system. When they say complex number system, they mean real and imaginary numbers are allowed. Okay, so we have the square root of -25. I'll do this one with you, and then you can try B on your own. So I would first notice that because it's an even index 2, a negative underneath is not possible. So this must be imaginary. I square root of 25. What does that mean? Well, the square root of 25, we know what that is. It's 5, isn't it? 5 times 5. So this is really I times 5. But multiplication order doesn't matter. It's called the commutative property of multiplication. So this is 5I, it means the same thing. So this could be written as 0 plus 5I. The real part would be 0 and the imaginary part would be 5I. That's technically how we write complex numbers, the real plus the imaginary part separately. But if you wrote 5I, we'd be okay with that. All right, try B on your own and see what you get. Okay, your first step, I almost can guarantee you pulled out an I because you saw a negative under the square root. Perfect. Now, when you're in this section, it makes sense. You've been doing it. But what if you're doing a problem 3 sections from now and all of a sudden you get a negative under a square root? You need to be able to remember that. That's really imaginary. Okay, so I times the square root of 12 is probably what you got. Okay, good. Did you break apart or simplify the square root of 12 correctly? Okay, let's check. Either you did 2 times 6 and continued breaking apart the 6, or you did 3 times 4 and continued breaking apart the 4. Either way is appropriate. So let's say you did 3 times 4. Most of my students go with 3 times 4. But you could have done 2 times 6. It's okay to be different. This would be 2 times 2 when you break 4 apart further. And we would say that the pair of 2's can come out. Now, where does it go? You might be wondering. It joins whatever's in front by multiplication. So I was in front. Now I have I next to 2, or 2 next to I. That really is 2I. Square root of what number? That's right, there is still a 3 trapped there. So if you wrote 2I square root 3, you're right. Perfect. Notice also you could have written, I don't recommend it, I'll tell you why in a moment, you could have written the real part first, 2 square root 3. and then you could have put the I afterward. That's the same thing. They're still being multiplied together, still next to each other. But the danger of doing it this way, even though I like to have I at the end typically, the danger is some students, maybe you, maybe not, I won't assume, but some students will accidentally extend that radical and they put I back underneath the square root, which is not correct. So that's why I would recommend leaving the I in front of your radicals. But if you really want to, play at your own risk. All right, take a look at C. There's a lot of negative signs going on there. Try to pause the video and try it on your own and then see how you did. Okay. Now, one of those negatives means take the opposite of the radical. That's what the negative in front said, right? The other negative underneath the radical tells you this is imaginary. So the first thing I would have done, maybe you didn't do it because we hadn't tried one just like it yet, I would have left the negative in front the way it is, but the negative underneath comes out as an I. So negative I square root of 11. The next thing I would have tried to do is to see if 11 could be simplified under that radical further. 11 is prime though, isn't it? Yeah, you can't write that as something times something. It's just 11 times 1. So if you wrote negative I next to the square root of 11, you are correct. The alternative, which again, play at your own risk, would be negative square root 11 and then I at the end by itself. They both are correct. Now what would be incorrect, I'm not going to say you did this, but did anyone out there maybe write the square root of 11? Maybe, because you saw a double negative and you're thinking, Professor, a negative times a negative is a positive. I know this. I've seen people say this to me. Now that is true, but keep in mind the radical is another operation. So this isn't a negative, it's not saying the opposite of negative 11, which is 11. It's saying the opposite of the square root of negative 11. Well, that's different, right? You can't say the negative is right next to the negative and turn it positive because that second negative is under the radical. So this is not correct. If you made that error, it's okay. I'm happy you made it now. Write in your notes that that is totally wrong and tell yourself why it's wrong. If you still don't know why it's wrong, come see me or email me. We'll talk. All right, let's take a look at our next slide and continue talking complex numbers and square root property. Example 2 says, use the square root property to solve each quadratic, which means degree 2, not degree 1, each quadratic equation. Now, when you look at these examples, it can be a little bit intimidating, I'm not going to lie. Earlier in the first slide, we just had a simple quadratic equation, like x squared equaled 9. That was nice, the good old days, right? We just said x equals plus or minus the square root of 9, which is plus or minus 3, and we were done. But now we have x minus 3 in parentheses to the second power equals 25. Now they've given you the method that they would like you to use. There are other methods that we're going to study in our future videos together, like the quadratic formula and then the completing the square method that we're actually going to talk a little bit about in this video. So there are other ways to do this. But for now, when they tell you the square root property to use that method, it's probably because it's the fastest one. And I would hope as you go through your videos and your homework and you prepare for your exams, that you start to ask yourself, looking at all the tools for how to solve equations that we study, what is the fastest way to do this problem? What's the most efficient way for me to use my time? And in this type of problem, the square root method is the most efficient because I have, get ready for this, something squared equals a number. Isn't that what the square root method said? Something squared equals a number. Okay, so if that's correct, if this is the square root property, doesn't that mean I can get rid of the power by taking plus or minus the square root of the other side? That's exactly what we said earlier. Feel free to go back to that first slide, x squared equals 9, same thing. Now we'll just have x minus 3 without the power of 2. So x minus 3 must equal positive or negative square root 25. Okay, what we've done now by using this square root property is we've taken a quadratic degree 2 equation and made it a linear degree 1 equation, which you should be able to solve by getting x by itself. So take a moment and finish this problem off and then come back and see if you got the right answer. So pause that video. Okay, let's see how you did. I would have noticed that that 3 could move over by addition. Add 3 to both sides. That might be the first step I would do next. Or you might have try to simplify root 25 as 5. Either one is fine. Eventually, though, you should be getting 3 plus or minus, and the square root of 25, that's just a pair of 5s underneath, so that's a 5 in reality. So this is like that birthday problem I was telling you about with my mom. I think she was turning 60, and I said 50 plus or minus 10. That means she might be 40, she might be 60, right? That was the idea there. Similarly here, we're saying 3 plus or minus 5. So what could these answers really be? 3 plus 5 would be what? Yeah, 8. That's 3 plus 5 if you're wondering where that 8 came from. What's the other option? 3 minus 5? Yep. And 3 minus 5 would be what? That's right, -2. So what we're claiming here is that there's 2 possible answers for x that would make this equation true. For example, if you'd go back into the original equation and replace x with 8, let's see what happens. 8 minus 3 is 5. 5 to the second power, 5 squared, 25, we're right. How about -2? -2 for x minus 3, watch your signs, that means it's -5. Not -1, right? -5. And -5 to the second power means -5 times itself, which is positive 25. Yes, they both work. In fact, the solution set would be the answers -2, we usually put the smaller one first, comma 8, right? Those would be the solutions. Okay, try B on your own, but notice to use the square root property, what did we need? Something squared equals number. If we don't see that right away, try to reorganize things so that you do have the same type of situation, the same template. Something squared equals a number. Okay, go for it yourself, and I'll meet you in a couple seconds. So pause that video. Okay, after you tried it, let's see if you got the same thing I did. Did you subtract 12 first? If you didn't, this would make the problem a lot harder, because if you try to take the square root of -4, you'd actually have the square root of x plus 2 squared plus 12 all under a radical. That would be a nightmare to deal with. So we want to first isolate the part that's being squared. Now this would mean I'd have x plus 2 to the second power on the left, and -4 minus 12 is really -16. You're welcome. I still gave you a nice number. Okay, now that you have something squared equals a number, you can pull the trigger on the square root property, right? So this is going to be the something, x plus 2 on the left, equals positive or negative, don't forget the positive or the negative, the plus or the minus, square root of this number, -16. Okay, let's see how you did from there. In the last part, we had x minus 3 equals plus or minus square root 25. We moved the 3 over by addition, the opposite, right? And then we simplified. Here, we do the same thing. Subtract 2, and you'd get x equals -2. Notice I put the -2 in front. You'll see why in a moment. It's usually better to put it in front of the plus or the minus. But if you wanted to write -2 at the end, it's also correct. It just looks a little wonky. Okay, -2 is being added or subtracted to the square root of -16. But wait, a square root of a negative is really imaginary. That's correct. That's an I. The square root of 16 is next to it. So I have x must equal -2 plus or minus I times the square root of 16. But wait, we can really simplify the square root of 16, can't we? Yeah, that's a perfect square. I gave it to you intentionally because there's a pair of 4s that produce 16. So this is really 4 next to an I, or 4i. So if you thought your answer was x could either equal -2 plus 4i or -4i, you were correct. X equals -2 plus or minus 4 copies of I. Now, when we get to understanding the meaning of these problems, we'll be actually talking about graphs which are parabolic in nature. Degree 2 equations are parabolic, and if it's x squared, they're opening up or down. These will turn out to be telling us the x-intercepts for graphs. When you get real solutions like we did in part A, we'd have an x-intercept at -2 and at 8. So those would be our 2 x-intercepts for a parabola that would be opening up, okay? In the second context, because we get imaginary solutions, while they're important, they're not telling us x-intercepts. To be x-intercepts for this graph, you'd have to be real, okay? So those will have different meanings. But keep in mind, in my note here, imaginary solutions like these in part B, they always come in pairs, and that's because of that plus or minus, Okay. So let's head over to our next slide where we now put all of this together with a process called complete the square, another way to solve quadratic equations. So the complete the square process, when I first learned this as a student, I heard square, 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 but no one showed me a picture. So I was really sad about that because one day I found out there's a visual way of understanding this that I think is very beneficial to some of you. So I decided to include a picture here for those of you who like pictures. Okay, so completing the square. We'll talk about the process, the algorithm, but we're also going to see why it makes sense. So let's take a look at the process. Completing the square, if you look at the box on the top right, it says we can complete the square for a quadratic of the form x squared plus bx plus c. Okay, and the way we're going to do that is notice, first of all, that the leading coefficient of x squared is a 1. Okay? If it's not a 1, we'll have to factor that in front, and we'll talk about that in our next video. But for now, we'll stick to the case where our leading coefficient's a 1. Okay. What we want to do is we want to find this magical number c. So what's really going to be happening in these problems is you're going to be looking for this. This is unknown. We're trying to find the magic constant c, which makes this called a perfect square trinomial. Now, we already know what a perfect square is. I've used that term a little bit today. A perfect square, when we talk about numbers, is a number where you can actually think of its roots as something times itself, right? Like 16 is a perfect square because it's really 4 times itself, 4 times 4. 81 is a perfect square because it's really 9 times itself, 9 times 9. But when I say a perfect square trinomial, trinomial means 3 terms, right? So what we're saying is you have a trinomial like, for example, x squared minus 4x plus 4. That's a trinomial. I claim that it's a perfect square trinomial, or a PST if you're in a hurry, because I could rewrite that as something times itself. In other words, it's a perfect square trinomial. Okay, so what times itself? Well, I'm going to claim that that's really x minus 2 times itself. Let's check. X minus 2 times x minus 2, or x minus 2 squared. If you FOILed it out, you can do this with me. X times x, that's x squared. X times negative 2, that's negative 2x. But doesn't it happen again here in the middle? Outers, inners last, right? Negative 2x and another negative 2x is negative 4x. And negative 2 times negative 2 is the constant positive 4. So yes, it's true that that trinomial x squared minus 4x plus 4 is in fact the same thing as x minus 2 times itself, or x minus 2 squared. Now, I may have just lost a lot of you. You might be thinking, why do I care about a perfect square trinomial? Totally understand. However, what we're going to be solving for is x in a lot of quadratic equations. And if we can find these perfect square trinomials, imagine if that was equal to a number like 9. Could you then use your square root property to solve it? Yeah, if I have something squared equals a number, I can take plus or minus the square root of 9, which is plus or minus 3, and that's what x minus 2 would equal. And then I move my 2 over and I get my 2 answers. So the completing the square process that we're about to talk about is allowing us to turn a trinomial like this, x squared plus bx plus something, into some binomial squared, which will allow you to use the square root property in our next video. Okay, so what we're going to do right now is we're going to talk about what is the process and why it works visually. So the process says to find this magical number, which we agreed was 4, right? So let's suppose we were trying to find that magical number 4. We didn't know what it was. We know the answer should end up being x minus 2 squared after we worked it out there. But let's see if we could figure that out ourselves. How would I have completed that square? Well, I would have completed that square by first taking half of b. So let's see what the process looks like in this example. Take half of b. Okay, what is b here? A is 1, a is the coefficient of x squared, b is negative 4, and c is unknown. We're looking for c in this problem right here. Okay, so for what we have is negative 4 for b. Can we take half of that? What's half of negative 4? Yeah, that's just negative 2. So if I take b and cut it in half, that's really negative 4 cut in half. If you want to multiply it by half, that's the same thing. That's dividing by 2, isn't it? So you get negative 2. Okay, great. What does that mean to me? Well, that means I'm going to go to step 2 now, and I'm going to square that number, and that will magically become the constant that I want. So the process is, if you want a simple way of saying it, take b, cut it in half, and square it. Take b, cut it in half, and square it. You can go to sleep saying that tonight. Take b, cut it in half, and square it. Well, what does that give you? It gives you 4. Hey, isn't that the magical number that we started with here? It is. So what we're saying is this process, if you're missing the constant to make it a perfect square trinomial, you can find that constant by taking half of b, which is the number next to x in this pattern, in this template, and you can square it and you'll have c, which will allow you to have a perfect square trinomial. Let's look at another one together, and I want to visually show you what's going on. When we say complete the square, we literally do mean you're completing a square. So here's what I'm saying. Suppose we have x squared here plus 6x. X squared plus 6x. Well, that's not quite a trinomial right now. It's just two terms, isn't it? Okay. So if we wanted to find that missing third term, this is the missing third term, this is like our c that we're looking for. If we're trying to find a perfect square trinomial, we need to find that c, don't we? So in order to do that, the pattern says take half of b. Well, what is half of 6? 6 divided by 2 is 3, isn't it? Interesting. Now, we know what we're going to do next. We know what the answer should be. According to the pattern, we square the 3 and we get 9. So we know this answer should be 9. Okay, so it should be 9. But why? Let's think about what this means. If we actually had a representation of x squared, could we think of that as a square where on one side you have length x? Let me see if I can, yeah, there it is, okay. There's this one side which is length x, and on the other side, again, is length x. Now I claim that if you remember, the area of a square or a rectangle was its base times its height, or its length times its width. So if you had a square which has side x and x, what is its area? So if you're talking about coloring in here, what is this area? It would just be x times x, or x squared, wouldn't it? So this could represent that square that we start with. So we have the square x squared. Awesome. And we're saying we're combining that with 6x. But notice in the process of completing the square that we learned in the box above, we said cut b in half. B was 6 here, right? 6 copies of x. If you cut that in half, you get 3x, don't you? 3 or 3x for each term. So that's really the same as 3x plus 3x, isn't it? So I have x squared, but now I also have 3 copies of x and 3 copies of x. Now, remember how a second ago I tried to interpret x squared as a square of sides x and x because x squared would be the area? Similarly, I could interpret 3x as a rectangle where one side is length 3 and the other is length x. And so here we see that for our 3, for example, that could be here, 3. And then our x, which we already had in red here, I'll be consistent, here. If I take that, interpret it this way, I see that I really have a rectangle where one side is 3 units long and another side is x units long. Or you could think of 3 little rectangles there, 1 times x, 1 times x, 1 times x. The areas you're getting there are just 3x when you add them up, because x plus x plus x is 3x. So yes, all of this area here would be 3x. Similarly, if you did the same thing, if you put those rectangles here, one side is 3 units and the other side is x units, once again, where x was this red side here, or you could put it on this side if you prefer. Then if you multiplied base times height, 3 times x, you'd get 3x again, wouldn't you? So this part, again, would have an area of 3x. So there's that other 3x. So we've started with the x squared area, which was the big square we began with. We've added to it two rectangles of area 3x apiece. Now notice we have this missing piece in the corner. If I wanted to literally complete the square, right? A square means you have the exact same dimensions on both the base and the height, the length and the width. Notice what we have so far. For the red square, it was length x, right? For the blue rectangle here, one of its sides was 3. But put together the way we've drawn it, what's the length of that entire side? X plus 3. Interesting. X plus 3, okay? But what about the other side? X was for the original square, and 3 was the length of the rectangle next to it. So together, x plus 3 is that entire distance. Okay, so x plus 3. But what am I doing here? I'm trying to find the area of the entire big square that I would have. And that would be if I multiplied them together, base times height. What would I get if I FOILed that out? X times x is x squared. 3 times x is 3x, and it happens twice. That's 6x. And 3 times 3 is 9. So what I'm getting is the missing piece must be 9. Right here, I need 9. How could I make that happen? Well, I could recognize that above here, I had a length of 3. So this must also be 3. I should have probably used blue so you could have seen the consistency here. This was 3 because the top part was 3, wasn't it? Similarly, this was 3, so this side is also 3. So if you have a square that it has units 3 by 3, what is its area? That's right, this area here is 9 square units because 3 times 3 is 9. And now we've completed that square. So the missing area was 9. Now, if you don't like that at all, you don't have to use that every time. You can simply remember the rule. Take half of b and square it, that's your missing term. Totally fine. But if you want to understand why we call it completing the square, it's because of this situation. We're literally completing the area of a square. All right, with all of that in mind, make sure you have the process written down somewhere. Let's head over to practice completing the square for our last example. Example 3, find the value of the unknown constant, here we call it n, in the last slide we called it c, needed to form a perfect square trinomial. In A, we'll do A together, or maybe we'll do B together. Try A on your own. Cut again B in half and square it and see if you can get your n. X squared plus 18x plus what would be our perfect square trinomial? How'd you do? Well, you would have taken B and cut it in half and squared it, right? So that would have been 18 is b, cut it in half, and square it. That's 9 squared. Did you get 81 for your third term, your constant? Yeah, if you got that n should be 81, you would be correct. What that means is the perfect square trinomial is x squared plus 18x plus 81. The way we'll be using this in our future video in the series will be, we're going to be trying to solve a quadratic equation by completing the square. So if you know that you need 81 on one side of an equation, you'll add 81 to both sides. And that will then allow you to rewrite this trinomial as something squared because it's a perfect square trinomial. What would that something be? Well, it's always going to end up being x times x to give you x squared. And then if you just take your b over 2 that you got here, which was 18 cut in half, right, was 9. So if you add 9 here, this should be the resulting binomial squared, x plus 9. So it's always whatever you got when you did b cut in half. 18 cut in half was 9. And you can check that, right? Go ahead and FOIL it out. X gets squared, you get x squared. 9x happens twice, so 9x plus 9x will give you 18x. And 9 times 9 will give you 81. So these mean exactly the same thing. That's the usefulness of this. And then we'll be using the square root property in our next video to continue from there. But for now, we're just asking you to try to find the missing term. We're building slowly our skills here. So right now, I just said, what would the missing term have needed to be? And you'd say 81, because half of 18 squared is 9 squared, which is 81. Now, where things get a little crazy is in B, because we are going to have fractions, and most Americans detest fractions. So we're going to have to get beyond that angst that we feel when we see a fraction and plod? Yeah, I'm looking for plod. We're going to have to plot our way through. All right, so take a look at this one, try it on your own, pause the video, and then come back and see if you got stuck or if you made it through. Okay, so the first step was to notice what b was, right? -7 is b. Take b, cut it in half, and square it. That's all we need to do. That's the process to complete the square and get your third perfect square trinomial term. Well, what does this mean? Well, -7 over 2 is getting multiplied by itself. You could write this as -3.5 if you like decimals better and use your calculator if you need to. But this is not terribly difficult if you understand how to raise a fraction to a power. You just raise the numerator to the power and the denominator to the power. Alternatively, you just multiply it by itself. -7 over 2 times -7 over 2. That produces a positive result. 7 times 7 is 49, and 2 times 2 is 4. Did you get 49 over 4? Maybe you did. Alternatively, you could have done -7 squared, which is 49, and 2 squared, which is 4, and you'd get your numerator and your denominator the same way. So what we're saying again here is this missing term should be 49 over 4, and we'll use that in solving equations in our next video. We'll add that to both sides and then use the square root property. Okay, so that might seem a little bit too much for you right now. What you need to focus on as you practice this material is, can you understand what an imaginary number is? Can you work with it effectively? And can you complete the square? That's it. So practice, because math is not a spectator sport, and I'll see you next time.